it's very, like, it allows you to do things at like a very sort of granular level. I found that it was a little more verbose and slightly more complex than Turf, but it's still a great project and still has a lot of great sort of functionality. So that's kind of an overview of the sort of geospatial libraries that we use. And what we do really is that we take these libraries and we kind of glue them together to really improve or attempt to improve our user experience. So what I'm going to do is I'm just going to give 5 examples of different ways in which we use these libraries, or just JavaScript in general, to improve the user experience and deliver value kind of using these tools. So the first thing that we do is we use, in this case, it's JSTS to tell a user, or to give some visual feedback to a user when a geometry is intersecting other geometries. And that's really important for us because essentially we never want there to be a case where we are delivering data to the mobile app, like mapping data that is like invalid or inaccurate, or I mean, it's as you can imagine, it's difficult to think of a scenario where a room would be intersecting into another room in real life. Like, most rooms are kind of joined together via a wall or via a door or something. They don't just tend to like intersect with each other. So that provides us with that ability to kind of prevent that from happening, and we give this big visual feedback to do that. And the way in which you do that is with JSTS. And JSTS can read in, has a GeoJSON reader, so it can read in the geometries. And then it has this intersection operation that you can use in the overlay class. And essentially we just pass those 2 read in geometries to the intersection, and then we check the area to see if it's we wouldn't, in a regular case, we would obviously check if it's just larger than 0, because if the intersection area is larger than 0, then there is some intersection. But we actually just check it against a very, very minuscule value. And the reason we just do that is because we saw a few issues with kind of like floating point errors, where sometimes it would say that there was like an intersection, and it would so unbelievably hypersensitive that if you had these floating point like rounding errors, then it would say obviously that's larger than 0, even though it's like an infinitesimally small number. So that's kind of how we do that. We use JSTS to provide visual feedback on intersecting other polygons. We also do a similar thing with self-intersection. So if there is if we are drawing geometry and we either draw or we drag vertices like into itself, so it's kind of self-intersecting, then we provide some visual feedback so that the user can correct against that, essentially. And again, that's just the same reason as before, is that we want to have like simple, valid geometries for the mobile app to consume. The way this just works is a little bit more complicated. We essentially check if we use JSTS to check if the geometry is like a simple geometry, and if it is, then we can just return false and say it's not self-intersecting. But then if for whatever reason that still continue, like, what we do then is that we check, we use something called the consistent area tester, and this is something that I haven't heard of before. Seems to be a Java topology suite. I don't want to say a specific thing, but it's the first time I've come across it. It was in this code base, and we use that to essentially check if that is what's called like a consistent area. And if it's not a consistent area, then we say that it's self-intersecting, essentially. So yeah, we just combine those 2 operations to make sure that the polygon is not self-intersecting. So the next thing I want to show you is snapping. So I'm sure some of you have probably seen snapping before in other tools like QGIS or ArcMap, or a whole host of other kind of different geospatial products. And I just want to show how we do that. So when we're drawing, like the principle of snapping is you draw, and then you if you go near another vertices, then it will snap to that vertex, essentially. And the way we do that is surprisingly, compared to some of the other operations we do, surprisingly straightforward. In that we, originally what I was doing here was trying to snap based on the distance, but obviously depending on how far you're zoomed in and out, the distance is going to be scaled differently. So what we found worked a lot better was just to do it on the pixel distance. So if you're drawing a point and it's near another point in terms of the actual pixel space, then you can snap those together. So what we do is that we just project the coordinates into the screen space, and then we check the absolute pixel distance between those two coordinates. And if it's bigger than some constant value, so I think we use like 40 pixels as our constant, then we snap to the point that's that is closest, essentially. And the cool thing about this is that we can actually change the snapping distance just by changing the constant, and that will provide a slightly different like end user experience. So in the future, if we wanted to, we could change that value to be like dynamic, so the user could drag a slider up and down, and that would change how aggressive the kind of the snapping was, which is would be quite cool, I think. Next thing I want to talk about is moving openings. So when we move a wall, or we move the bounds of, say, for example, a room or a walkway, we have to move the opening, because the opening isn't actually like topologically linked to the parting wall, if that makes sense. It's just a geometry. It doesn't have like any it's only linked by like a referential ID from the opening, the first room and the second room. It doesn't, it's not linked topologically. So we have to move that opening. And this code's a little bit more dense, but the exciting part, or the thing that the core of it is essentially in this bottom block here, line 14, where we use the turf slice along functionality. And essentially what this allows us to do is say, we take a line and we take some point along that line to start sort of drawing or start creating a line, and then we take some other point along that line to stop drawing the line. And that allows us just to create a new line across the wall that gets moved the same length as it was previously. And we use that to basically just move the line to the new position of the wall, so wherever the wall has been positioned to. So the last thing I want to touch on is generating routes. So one big problem for us is that at the moment we have to, or users have to draw out each individual route in the building or in the supermarket, for example, and draw out all the possible routes that are used, like the end user and the hyper app could take. This is fine and it works, but it's a bit time consuming. So one thing we would love to be able to do is just generate all the routes, like use algorithmically just generate routes for users, essentially. And the way I have a work in progress of this, and I have something like semi-working, and essentially the way that we do that is we triangulate all the rooms, and then we take the midpoint of all of the inner sort of triangle lines. So you'll see on this top right hand image, if you imagine there was a midpoint across all of those red lines that are coming out, then that allows you can draw lines between those midpoints and basically create routes that are valid and within inside the room. The one problem that we have is that those that basically we generate routes between those points using a thing called GeoJSON Pathfinder, which is it's a GeoJSON based shortest path library, which is open source. but what we found is that it was generating routes that were like too optimal, if that makes sense. Like it would cut across corners like way too close to the wall, or way too close to corners of a room, in a way that, like, as a human being, like, you would never walk like 3 millimeters away from a wall. Like you would always be walking like a meter away from a wall. So yeah, we've still got a bit of work to do there in terms of like essentially making those routes more human and making them more sort of orthogonal, and centering those routes to be more to kind of just make them more how you would walk in real life, essentially. But that's something that we're looking at. So yeah, in the future, I'd love to spend more time getting TURF working with TypeScript more, and just leveraging the actual TURF, because TURF is like a modular framework, so you can just pick and choose the modules that you want. But I've just kind of been using it at just importing the whole thing. But I'd love to kind of use it in a more modular way. I'd also potentially like to see if there's a way to implement some of the things we're doing with JSTS with TURF. Like I struggled to get TURF working in a way that produced a good end result, but I'd love to maybe revisit that at some point. And we'd love to look at potentially open sourcing some of the more modular parts of the code, some of the parts that we think are relevant potentially to the community. And we'd also potentially love to look at putting stuff on a different thread to make it, because a lot of those operations are quite intensive. So it'd be great if it was running in a separate thread, so it wasn't blocking the user interface whilst those operations were going on. And so another thing alongside that is potentially looking at WebAssembly, which is something that I spoke about last year at FOSS4GUK, and seeing if there's a way that we could potentially leverage WebAssembly to give some performance improvements, or to make that more sort of consistent and stable in terms of its running times. So yeah, takeaways. I guess the main points that I wanted to make here was that both TURF and JSTS are very powerful and kind of easy to use geospatial libraries that you can use in your application today. And they don't just have to be for you know, the core business features. They can be, we use them more actually for sort of improving the user experience and making sure that for example, our data stays valid. And sometimes you don't even need a library at all. So for example, with our snapping section of our code, we don't really use TURF for that. We just use like a Cartesian distance formula that you know, you can find that online. It's just on Wikipedia to find the distance between 2 points. And lastly, that there's loads of more niche libraries out there. So for example, the GeoJSON pathfinding library, there's lots of smaller open source libraries for solving very specific problems such as routing.
James, I'm going to stop you and say
great.
Thank you, just because I want to get a couple of questions in, and I don't want us to lose the time.
No problem.
So from Joe London, what's your opinion of using TypeScript in relation to typing geometries, and which geospatial libraries are well integrated with TypeScript? Yeah,
it's a really great question. So to my understanding, so yeah, I love TypeScript. I'm a big fan, as you can probably see, as we use it both on the front end and the back end. I think it's really helpful from a geometry perspective, especially with like GeoJSON, because sometimes it can be quite hard to remember the order of the sort of the properties and how nested they should be and things like that. So with TypeScript, if you create a geometry that, for example, is like has a property in like the wrong place, or doesn't have enough, the coordinates aren't like nested enough, then it will just tell you like, this isn't a valid polygon, this isn't a valid line, for example. And that's really powerful for us because it saves me a lot of time with having to faff around trying to understand why Mapbox is exploding because the geometries aren't in the right shape or the right format, if that makes sense. In terms of libraries, I would say, so to my understanding, Turf has TypeScript support. I haven't, if you use it as the whole library, I've struggled to get that working as you would expect. I have to just kind of hack around that, so to speak, and just type it as like any, which just means that it's untyped. But apparently if you use it in a modular way, each of the modules should have their own TypeScript definition. So it should provide you with all of the types that it requires. And that's great because it means that if I say like, give me the union of these two geometries, it will tell me like, okay, well, the first geometry you put in has to be a polygon, and the second geometry you put into this function also has to be a polygon. So if you try and put in a line and a line, then it will, before you've even run the code, it will show you like this is erroneous, so to speak. JS, sorry.
Thanks. Jez wanted to know, have you used this for server-side programming or only in the browser?
Yeah, so we do use Turf. The root generation stuff we were talking about, we do that on the server. So yeah, you can use Turf on the server. I think actually it's a bit underrated because you could potentially move a lot of stuff out of the client if you wanted to, and just run it server side. So yeah, Turf works with Node. I don't know if JSTS works with Node. I would assume it does because it's JavaScript. So I would hope that it would work alongside Node, but I haven't tried it, so I can't say for certain.
And the last question that I've got time for is, how are you going to record user indoor positions and routes? By 5G or question mark?
Yeah, we use Wi-Fi based positioning, and we also use we augment that with some of the AR stuff that we're doing to give a more accurate position. So it's a mixture of those two things essentially. But that's more on the I'll be honest, that's more on the app side, so it's not my area of expertise. But
right.
Yeah, hopefully
that's
that
the
gives some
secret
insight.
sauce.
It is the secret sauce, yeah.
Okay.